Thank you, John. Hello, everyone, and welcome to this second keynote. I'll be talking about the major theme of this year, which is C++20. And in this keynote, I will be giving a high-level overview of almost all new language and library features added to the C++20 standard. So without further ado, let's get started. But first, a little bit about myself. I'm a software architect for Nikon Metrology, and I'm based in Belgium. I'm a Visual C++ MVP since 2007 and author of a couple of books, and I'm happy to announce that the 5th edition will be coming out later this year. The 5th edition of Professional C++ will be coming out later this year, and it has been updated to include all C++20 features. And I'm also the founder of the Belgian C++ users group, and we try to organize like 3 to 4 user groups events per year. So let's get one thing straight. C++20 is a major update. It's big. There are lots and lots of new features. I think it's even bigger, or at least as big as C++11. And good news, on Friday, September the 4th, so 1.5 weeks ago, the C++20 standard passed ISO voting, so we expect it to be formally published by the end of 2020. What will I be talking about? So first, I will be touching on the 4 major new features, which are modules, ranges, coroutines, and concepts. Then there are a couple of changes to how Lambda expressions work, changes to constexpr functions. There is new functionality for writing concurrent code. And finally, there is a whole lot of other smaller features and changes to both the language and the standard library. So I'm not going to read this whole list right now, but we will be touching on all of these topics briefly during this keynote. But this session, obviously, since I have a lot of topics here, obviously it's a high-level overview, so I will not have any deep dive into any specific feature here. But there are other sessions this week that will cover specific features from this list. And if that is the case, there will be a small green rectangle on the slide with a reference to the session, which you can follow to get more detailed information. All right, so there are a couple of new keywords added to the language. First, we have concept and requires, and these 2 keywords are used in the context of the concepts feature. We have constinit for constant initialization. We have consteval for constant evaluation. And then we have 3 keynotes related to coroutines, co-await, co-return, and co-yield. And finally, one last new keyword is char8t, and that one complements the char16t and char32t that have been added to the C++ standard with C++11. There are also 2 new identifiers, namely import and module. And what is the difference between a keyword and an identifier? A keyword you cannot use anywhere. An identifier is reserved only in certain contexts. So for example, you could have a variable name with the name import, but in certain contexts, that is a reserved word. Previously, we already had some identifiers and they were final and override. All right, so let's get started with the first major feature of C++20, modules. What are modules? Modules, basically, they will replace header files on the long run. And with a module, you have to explicitly state what you want to export from the module. For example, you have to say which classes, which functions, which constants, which enumeration classes, and so on you want to export. And only this exported functionality will be available for users that import your module. Then there is the concept of a module interface file and a module implementation file. So you could separate your code into an interface file and an implementation file, just like you did in the past with header files and CPP files. But with modules, that is not a strict requirement anymore. Because for a module interface file, only the function signatures are part of the exported interface. So even if you write any function body in a module interface file, that will not be exported, or that will not be in the exported interface. So if you modify that body, you will not trigger any rebuild of users that are importing that module. And that was one of the drawbacks with header files, if you implement your functions inside your header file, whenever you modify the body of your function, you trigger a rebuild of everybody that is including that header file. That is not the case with modules. Still, I think in certain cases, it's a good idea to separate your module interface file and your code inside a module implementation file, because that way your interface files stay clean without any implementation details. If you want to add more structure to your module, there are two things you can do. You can either use submodules or you can use so-called partitions. And the nice thing about modules is that you don't need any include guards anymore. You don't need to invent unique names. If you have two modules that have the same name, these two names will not clash. They live in their own module. Of course, if you import these two modules in another source file, then you will have a linker error. Another interesting aspect of module is that they are processed only once, so this will result in faster build times. And also, preprocessor macros will never have any influence on the code inside your module, and any preprocessor macros that you have defined inside a module will never leak from that module. And because of this, the order of module imports is not important. And this was important with header files, because it could be that one header file defines some kind of preprocessor macros that was important for the next header file that you include. So let's have a quick look at how you write a module. So here I have a module. It's in a file called cppcon.cppm. And the module starts with a module declaration, which just gives a name to this module. Next, I define a namespace with two methods. The first one, getWelcomeHelper, is not exported and it just returns a string. And the second one, getWelcome, is exported and basically just forwards the work to the helper function. How to consume this module? Well, you simply do an import CppCon instead of any hash include. And then once you have done that, you can start using the exported functionality. So here at this location, I will not be able to call getWelcomeHelper. So C++20 provides all the machinery for support for modules, but it does not specify if and even how to modularize the standard library itself. But all C++ headers in the standard are so-called importable. So instead of writing hash include version, version is one of the new C++20 headers. So instead of writing hash include version, you can simply write import version. What this does is everything that is in the version header will be implicitly exported, including macros. This is different compared to writing your own modules, in which case macros are not exported. But if you import these headers, then all macros will be exported as well. And just by doing this, instead of writing hash include version, you write import version, you will improve your build throughput, because now this version module will only be processed once. So you can think of this as some kind of compiler-independent precompiled header file feature. So on Friday, there is a session by Timur that goes a little bit deeper on this feature. And it's also possible, as I explained with the C++ headers, they are importable. It's also possible to make your own headers importable, but how to do that is compiler dependent. So please check your compiler documentation to find out how to do that. The next big feature is ranges. What is a range? A range is basically an object that refers to a sequence of continuous elements. So basically, it's kind of like a begin and end iterator pair, but it's not the goal of the range to completely replace all begin iterator pairs, and it will become clear with an example. So why do we want the range? Here I have a vector of data, I have 3 elements, and I want to sort these elements. So how to do this? Before C++20, you use the sort algorithm that is available in the standard library, and you just pass a begin and end iterator pair, and then the whole range will be sorted. But in this case, I really want to sort the whole container. So with ranges, you can really just say ranges sort data, and my whole range, my whole container will be sorted. Nice thing about this is that it's impossible to have mismatching begin and end iterators. For example, I could call the sort algorithm and pass it a begin iterator of one container and accidentally pass it the end iterator of another container, the compiler will not complain, but of course it will not do what you expect at runtime. With ranges and the algorithms that support the ranges, you cannot make these mistakes. And additionally, there is the concept of range adapters that can lazily transform or filter your data before it is passed to any algorithm. And we will see an example of that later. There are a couple of major components that you need to know about when working with ranges. So first, range itself, that is defined as a concept that defines the iteration requirements. And all of the standard library containers that support begin and end, they are valid ranges. Next, we have the range-based algorithms. So almost all standard library algorithms that previously accepted iterator pairs, they are adapted to also accept ranges. And a lot of these standard library algorithms that accept a range now, they also accept a so-called projection. And a projection is basically a callback that can transform the elements from your container before they are handed over to an algorithm. Next, we have a view, and a view that is basically the transform. A view can transform and filter a range, and all of that is lazily done. A view does not own anything, and a view can also not modify the underlying elements. And we will see an example of that on the next slide. Range factories can be constructed to produce values on demand. For example, a range factory exists that generates an infinite sequence of integers. We will see an example of that as well. And finally, pipelining allows you to pipeline several transformations or several filter operations in a nice so-called pipeline. Let's see how this pipelining works. So here I have a vector of data. I have 10 integers. And as we saw on the previous slides, the vector supports begin and end operations. So this is a valid range. So we start with our range, the complete range. Next, we apply a so-called filter operation. And what this filter operation is doing, it will filter all the odd elements, resulting in the following data. We only keep the numbers 2, 4, 6, 8, and 10. Next operation in our pipeline is a transform operation, and this transform operation is just doubling all the remaining elements in our range. So we get 4, 8, 12, 16, and 20. We drop the first two elements, so we get 12, 16, and 20. We reverse the elements, and finally we transform them again, and we convert the remaining elements in our range to strings. So the result is 3 string elements representing 20, 16, and 12. So what you can see here is that transform does not always have to transform a certain element to another element of the same type. So in the first transform here, I'm transforming my double into another double, but here I'm transforming it into a string. So just by constructing this result object here, nothing has been evaluated yet. Everything is done lazily. Only at the moment when I iterate over the elements in my result object, at that moment, the whole pipeline is executed. And because all this is lazily executed, we can work with so-called infinite sequences. So here I'm using a range a range factory, and this one is creating an infinite sequence of integers starting with 10. And I can just do anything what I want with this infinite sequence of elements. I can filter it, I can transform it, I can drop elements, reverse elements, everything what you want. And finally, I'm just taking the first 10 elements here to limit my final result. Because of course, if you're working with infinite sequences and I would be iterating over the result, that would result in an infinite loop. So somehow you need to limit your elements in the range. And in this case, I'm just taking the first 10 elements of the final range. So on Thursday, there is a session about ranges given by Tristan if you're interested in a more deep dive. The third major feature is coroutines. What is a coroutine? A coroutine is a function, but not just any function. It's a function that contains one of the three keywords: co-await, co-yield, or co-return. Co-await suspends my coroutine while it's waiting for some other asynchronous computation to finish. Co-yield, it returns a value from my coroutine back to the caller. It suspends my coroutine, and subsequently, when the caller calls my coroutine again, it is resumed at the statement after co-yield. And finally, if you want to really stop your coroutine, if your coroutine is really finished, you can do a co-return. You cannot in a coroutine, you're not allowed to just use the return statement, you have to use co-return. Coroutines, what can they be used for? Well, they can be used to write so-called generators. We'll see an example of that on the next slide, but they can also be used for asynchronous I/O, for doing lazy computations, event-driven application, and much more. However, with C++20, the standard contains all the language additions, all the machinery needed to support coroutines. So you can write your own coroutines, but the standard library does not yet include any helper classes such as these generators or asynchronous I/O. So we first want to get some more real-world experience with working with coroutines before any of these helper classes are standardized, maybe in the next C++ standard. And the thing is, writing these coroutines yourself is actually pretty advanced, and you need to know what you're doing. So if you want to use coroutine, at this moment, I suggest that you search for some existing libraries that provide you some coroutines instead of writing your own. So Visual Studio comes with an experimental helper class called a generator, and let's see how that one works in practice. So here we have a simple coroutine, and the coroutine, it just contains a for loop that starts at a given starting value that iterates a number of times. On each iteration, it just gets the system time, it outputs the system time to the standard output, and then finally, it yields the current iteration value. In main, we just call our coroutine, which returns you the generator, and then main iterates over the values produced by the generator. And on each iteration, it outputs the value given by the generator and then waits for the user to press enter. So the first time when main asks for the first value from my generator, my coroutine starts executing the first loop until it reaches the co-yield. Then the current I will be given back to main, which outputs it to standard output, waits for the user to press any key, and then my main asks for a second value generated by the generator, in which case the coroutine will resume executing right after the statement of co-yield, and then it just starts the next iteration, and so on. So the output is as follows. The first output that I get is the date and the value 10, and then every time when I press enter, the next iteration of my coroutine executes, yielding the next value, and main outputs that one to the standard output. There are a couple of sessions. There's one on Tuesday and one on Friday if you want more information about coroutines. And the fourth and final big new feature in C++20 is concepts. Concepts are requirements, named requirements, to constrain template parameters of either class templates or function templates. And they are predicates that are evaluated at compile time, so they don't have any impact at runtime. Let's have a look how we can create a simple concept. Here I'm creating a concept called incrementable, and I'm requiring that a type T supports both the postfix and prefix operations. So what this statement says is basically that for a type T, x++ and ++x should compile. So this is not code that will be executed at runtime. This is code that is evaluated at compile time. How to use this concept? A first way to use this concept is, instead of writing type name T, I can just say incrementable T. That's one way. Second way is to use a so-called required clause. And you can just use type name t requires incrementable t. The requires clause can be either before the function signature or after. And maybe the cleanest way to use it is to combine it with abbreviated function template syntax. And then you get the following syntax. You just say incrementable out of t. So you don't have to specify any template line here. Of course, this is a very simple concept here. So let's look at how you can make some more powerful concepts. And let's write a concept that requires a non-throwing swap method and that requires a size method that returns a size t. So since I want to say something about swap, that means I will need two parameters. So we define our concept with two parameters, in this case, two references, x and y. Once we have these, we can say, or we can require that x.swap_y compiles and is marked as no except. We can also say that x.size compiles and returns something that is convertible to a size t. And we can have as many requirements as we need here. We can also combine existing concepts. And one way to do this is using the requires clause. So we can say something like this. We have a template with one template parameter t, which requires that t is incrementable and decrementable. That's one way to combine concepts. Of course, you can also just create a new concept. I'm creating a new concept C, which is incrementable and decrementable. And once we have this one, you can just use again the abbreviated functions template syntax to use this new concept. And in the case of concepts, the C++20 standard library actually does define a whole lot of predefined concepts. So we have things like same, derived from, integral, constructible, convertible to, and also more high-level concepts like sortable, mergeable, permutable, and much, much more. There are a couple of dozen different standard concepts that are available. So I suggest if you need a concept, first check what exists in the current standard library. And if it doesn't exist what you exactly need, maybe you can use a combination of existing concepts instead of writing your own concept from scratch. And one big benefit of using concepts is that they help the compiler with producing better error messages. Let's look at an example. I have here an abbreviated function template that requires t to be incrementable. And next I define a class bar that doesn't define anything, so obviously this one does not satisfy the incrementable concept. And then in my main, I'm just constructing a bar and then calling my foo with an instance of my bar. Instead of any cryptic template error messages, what I get is a very clean error message from the compiler. It simply states that I cannot call foo with a bar because bar is not incrementable. And everybody that has worked with templates, especially more complicated templates, if you provide the wrong types for those templates, then you might have like hundreds of cryptic template error messages. Then you have to hunt down to find the location in your code that is causing the error. And concepts will help a lot here. There are 2 sessions, one on Friday and 2 parts on Tuesday if you are interested in more content about concepts. There are a few changes to Lambda expressions. The first one is before C++20, if you capture everything by default by value, that would implicitly capture this. This is not the case anymore. So since C++20, you need to explicitly state that you want to capture everything by value and that you want to capture this. So this might be a breaking change for certain code bases. Next is that we have support for templated Lambda expressions. And the syntax is, as you would expect, you just use type name t or any number of template parameters you need, and then you can use these template parameters inside your Lambda. Why do we need this? So first example is suppose you have a generic Lambda that accepts a vector of t, and you want to know the type of t. Before C++20, what you have to do is you have to use some decal type and dkt voodoo. First, you have to do dkt decal type vec, and the result of this gives you the vector of t. And once you have this vector, you can ask the value type of the vector, and that gives you the t. And then once you have the t, you can do whatever you want with the t that you want to do. With C++20 and a templated lambda expression, you don't need any of this decay and decal type and this type name and nested type alias and so on. You can simply say type name t, and then use, instead of autoref, you can use a constant vector tref. And then you have direct access to the t in the body of your lambda expression. And a second motivation is if you have a lambda expression with a variadic number of templates and you want to forward these variadic set of parameters, if you want to forward these to another function foo, you had to use decal type again. So you have to use forward decal type of the arguments. With C++20, you can drop the decal type, as you can just use a templated lambda expression with a variadic template pack. So before C++20, if we have a simple capture that was followed by an ellipsis like this was a pack expansion that worked perfectly fine. But if you had an init capture like this, args equals submove args ... this was ill-formed in C++17 and older. Now with C++20, this is well-formed, and it does exactly what you expect it to do. Changes to constexpr. So now virtual functions can be marked as constexpr. And a constexpr function can now also include calls to dynamic cast, can use type ID. They can now actually do dynamic memory allocations using new and delete, but there is one caveat here. And you need to make sure that you're using the global new and delete functions. And also anything that you allocate in your constexpr function, you need to make sure that you deallocate it in the same constexpr function. And finally, try-catch blocks are now allowed, but a constexpr function is still not allowed to throw exceptions. So it has to catch all the exceptions that could be thrown. And with all these changes, it was possible to make both string and vector constexpr. So now you can use string and vector in your own constexpr functions. And this is the first step to, at one point, support constexpr reflection in the future. There is a session on Tuesday by Stefan that will go a little bit deeper on this topic. Concurrency changes. Let's talk a little bit about shared putter. Is shared putter thread safe? On the one hand, yes, the control block manipulation is thread safe. So basically, incrementing and decrementing the reference count is thread safe, and this guarantees that the object is deallocated exactly once. What is not thread safe is accessing the pointer, because one thread could be reading the pointer and another could be storing a new pointer. So that is not thread safe. Can we make it thread safe? Of course. We can manually use a mutex to protect access to the shared pointer. Or we can use the global non-member atomic operations like atomic load, atomic store, and so on. But this is error prone, and I will show you on the next slide why it is error prone. With C++20, we have now support for atomic shared pointer. Of course, internally it might still use a mutex, but you don't need to worry about that. And additionally, these global non-member atomic operations have been deprecated. So let's look at an example. Here I have a concurrent stack using the C++20 atomic smart pointers. So one of the members is an atomic shared putter. And wherever I'm using this, for example here, I have to do something like head.load or head.compareExchangeWeek and so on. So I cannot make any mistakes. I have to use methods of my atomic shared pointer whenever I want to do something with that shared pointer. While with C++11 or C++11, I would not use an atomic shared pointer, but just a shared pointer. And then instead of head.load, I have to use the global non-member function atomic load. And here also I have to use the global non-member function atomic compare exchange week. But you see, there is nothing that really prevents me from directly using the shared pointer. And if you do that, then again, it's not thread safe. So C++20 safeguards you, and it makes sure that you cannot make a mistake actually. C++20 adds support for joining and cancelable threads, so there is a new thread class, JThread. It also lives in the thread header file. And this one has two new features. One, it supports cooperative cancellation, and two, the destructor will automatically cancel the thread and call join. And why this is important, we will see on the next slide. How to cancel thread? There are three aspects here. You have a stop token, and a stop token is used to actively check if a stop has been requested. So a thread that supports cancellation will have to periodically check if a stop is requested, and that's why it is called cooperative cancellation. It requires work from the thread itself. The nice thing is that stop token is compatible with condition variable any. So if your thread is sleeping on some condition variables, it can be woken up by a condition variable any when a stop token is raised to stop the thread. The second is a stop source, and the stop source is the other side of cancellation. Stop source is used to actually ask a thread to stop. And finally, we have a stop callback. You can register a callback, and then your callback will be called whenever a stop is requested. So let's have a look at how this changes how you write your certain code. So here I have a function that creates a thread object. It's doing some work. And in parallel with the work that this thread is doing, I'm doing something else. But I'm using the old thread object here. So we have to be careful here, because if the thread object is destroyed while it is still joinable, then your application will terminate. So I have to make sure that I call join at all the points in this function where it can where the function can go, where the function finishes. And of course, my do something else can throw an exception. So I have to wrap this whole code inside a try catch block. In the catch, I have to catch all the exceptions. I have to make sure to call join on my thread and then just rethrow the exception. Of course, in the case do something else doesn't throw any exception, I have to make sure that I join as well in that case. So this is quite a lot of ugly boilerplate code. With a JThread, I don't have to write any boilerplate code. I just construct my JThread as follows, then do something else. I don't need any try-catch blocks. I don't need any manual calls to join, because the destructor of JThread will automatically, one, cancel the thread, and two, call join on the thread. So how is this cooperative cancellation working? So whenever I construct a JThread object, the first parameter of my thread function can be a so-called stop token, and then periodically your thread can check the token for a stop that has been requested, or can use a condition variable any to get woken up when the stop token is triggered. And then somewhere else in your code, you can say that the job should stop. You can also ask for the stop source, and then you can ask the thread to stop through the stop source. And finally, you can ask for a stop token as well, and then you can, through the token, you can figure out whether a stop has been requested or not. C++20 includes a couple of new synchronization primitives, and the first one is a so-called semaphore. That's a very lightweight synchronization primitive. And this one can actually be used to implement almost any other synchronization concepts, such as mutex, latches, and barriers. There are standard supports two types of semaphores. One is a counting semaphore, and the other is a binary semaphore. For example, a binary semaphore has just one slot, and this slot can either be free or not free, so this is perfect for implementing your own mutex. Next, we have the latches and barriers, though they help with thread coordination. A latch, it's a coordination point in a thread. So a thread blocks when it arrives at a latch point until a given number of threads arrive at that point. And then once the number of given threads arrive at the point, then all of the threads are unblocked and continue. So basically you say that at the coordination point, I want 5 threads to arrive. With each thread that arrives at the coordination point, a counter is decremented. Once the counter reaches 0, then all the threads are allowed to continue executing. Once the counter reaches 0, it stays 0. So basically a latch is a single-use object. If you want multi-use, you can use a so-called barrier. That is it contains out of a number of phases. So again, we have a number of threads that block until a requested number of threads arrive at a certain point. And at that point, some kind of callback is executed. The counter is reset, the next phase starts, and all the threads can continue. We also have support for atomic reference now, and they are, sorry, that was the next slide. So we can, STD atomic has been augmented with 3 new methods, wait, notify one, and notify all, and they allow you to wait for an atomic object to change its value, and this is more performant than polling. And finally, atomic reference. So basically, it's the same as an STD atomic, but it works with references, while an STD atomic always copies the value that it is provided. So in certain cases, atomic reference can be more efficient. And then there are lots of more smaller changes. First one, we have so-called designated initialization for aggregates. So here I have a simple structure containing an integer and a string. And designated initialization means that you can initialize it based on the name of the member. So you write dot a string is hello. Anything that you don't initialize will keep its default values. Another one is Spaceship Operator. Officially, it's called three-way comparison operator. And basically, with one operator call, you can figure out whether an object is less than another object, equal to another object, or greater than another object. So it's kind of similar to the old C-style string compare, which returns a negative value, 0, or a positive value, depending whether the first string is less than, equal, or greater than a second string. If you want to add support for the Spaceship Operator to your own classes, you can simply write one single line like this, and you can ask the compiler to implement it for you. Just by writing this single line, the compiler will generate all 6 comparison operators to compare x and y, and it will do the comparisons member-wise. And I say all 6, so just by writing this single line of code, it will also generate the equality operator for you. Of course, you cannot always let the compiler do the member-wise comparison. In that case, you should implement the Spaceship Operator yourself, which means it won't be defaulted, which means you also need to write your own operator equal. And if you write your own, you have a choice of 3 kinds of return types. You have a strong ordering, partial ordering, and weak ordering. Not going into all the details here, what the difference is between them. How to use it? So here I'm just an integer, and I want to compare that integer with 0. So I just use a Spaceship Operator to compare it with 0. And with this one operator call, I know whether 42 is less than 0, greater than 0, or equal to 0. And you can verify the result, or you can analyze the result with this syntax. Additionally, there are named comparison functions. So instead of writing something like result equal strong ordering less, you can just use the name comparison function is less than result. This has quite an impact on the classes that you write. In C++17, if I had a point class with a simple x and a y member, and I want to support all 6 comparison operators, I have to implement all 6 of them. Of course, once you have equal, and less than, the other ones you can implement in terms of these 2, but you still need to implement all of them. In C++20, you simply include the compare header, and you ask the compiler, do all the work for me, which in this case works because member-wise comparison of x and y is exactly what we want. The standard library has full support for the Spaceship Operator, so all the classes like map, set, vector, string, all of them support the Spaceship Operator. And actually, if you look at the diff of the standard document itself, you can see that, I'm looking here at the vector class, you can see that operator Spaceship has been added, but it's not defaulted, so that means we need to keep operator equal, but all 5 other operators have simply been removed. In C++17, initializers for switch statements were added. So basically the syntax is as follows. You can initialize any kind of variable you want here, and then it's available here and in the body of the switch statement. Similar, C++17 has added support for initializers in if statements. Same syntax, you can initialize any variable you want here. It's available in the expression here and in the body. And now C++20 added support for similar initializers in range-based for loops. Again, using the same syntax, you can just initialize any variable you want here. It's available in the expression here and in the body. Non-type template parameters. In the past, you had quite a lot of limitations. So you cannot use classes, you cannot use floating point types. These limitations have been relaxed, and now floating point types are allowed, class types are allowed, but class types are allowed with quite a lot of restrictions. And one example use case is the CTRE library, the compile time regular expression library. And thanks to non-type template parameters, the lifting of the limitations, what that library is able to do is you can construct a match object and pass it a regular expression as a non-type template parameter. And by writing this, the regular expression is parsed at compile time, and your match object is constructed at compile time instead of at runtime. There are two new attributes added to the standard. We have likely and unlikely, and they allow you to give hints to the compiler for certain optimizations. So in this case, if you know that case 2 is much more likely than the other cases, you can put an attribute there. If case 3 is less likely than anything else, you can put an attribute there. And the same thing can be done with branches of if statements. The Chrono library has been extended with quite a lot of features. First, calendar support has been added. At the moment, only the Gregorian calendar is supported, but you can add your own custom calendars. And when you do that, they will interoperate with anything else that is in Chrono. So let's have a look how you can create a year. You can either use the constructor syntax, or you can use a standard user-defined literal. A month can be constructed with a constructor or with one of the 12 predefined instances. And you can create a day similar like a year. You can just use a constructor, or you can use a standard user-defined literal. These just create a single year, a single month, and a single day. But of course, you can create a full date as follows. One of these two syntaxes you can use. And additionally, you can say something like this. I want to create a day that is the 3rd Monday of September 2020. There are a couple of new duration type aliases. Before, in C++11, we already had seconds, minutes, hours. Now we have also days, weeks, months, and year. So if I have, for example, an object that represents 1 week, I can convert it to days. Besides the system clock, static clock, and high resolution clock that were already in the original Chrono library, we have 4 additional clocks now. They are very specific. They have very specific behavior. I'm not going in all the details here, but it's just so you know that there are additional clocks in case you ever need them. One new type alias is systime, and that is a time point of a system clock with a given duration. And based on this systime type aliases, there are 2 new type aliases, sysseconds and sysdays, and these can be used as follows. So here I have a date. I have 15th of September 2020, and thanks to the sysdays type alias, I can convert this to a time point. The other way around is also possible. If I have a time point, I can convert it to a date using this syntax. And both of these examples are working with a resolution of a day, because here I'm rounding it to days, and here I'm using the sysdays type alias, so resolution is a day. Of course, you can combine date and time. So here I'm constructing a date, 15th of September 2020, and 9 o'clock in the morning. So by doing it like this is actually a UTC time. Once I have this, I can convert this to any time zone in the world. So with this syntax, I'm converting my UTC time to the Denver time zone. I can also ask what is my current zone, and I can ask the system the current time of the system clock and then create a zone time. And finally, if I want to output any of these times, you can just use the insertion operator like this. Next feature is span. A span provides a view over some contiguous data. A span does not own anything, so it will never allocate and deallocate. Basically, it's just a pointer to the first element of the continuous data and the size of the data. So that's also why it's very cheap to copy, and it's recommended to pass them by value, just as you do with a string view. And also, unlike string view always is a read-only view of a string, but a span can be either read or write, and we'll see an example of that. A span can be either dynamic sized or fixed size. So here I have a C-style array, and I construct a span over that with type int and size 42, so this is a fixed size span. If I construct my span as follows, I don't specify the 42, then it's a so-called dynamic size span. If I provided the wrong size, for example 50, while I only have 42 elements, then I will get a compilation error. If I have a pointer and a length to some part in memory, I have a dynamic sized span. And all of these spans are read-write. So through the span, I can modify the elements in my data array. If you don't want that, and you want to construct a read-only span, you should construct a span of const int and not a const span int. And a span supports quite a lot of operations. So of course it has full support for iterators. So you can ask begin and end iterator and so on. You can ask for the first element, the last element. You can access any element in the contiguous data using the square bracket operator. You can ask for the size in bytes. You can ask for a subspan. You can ask for the first number of elements or the last number of elements, or even a certain subspan in the middle of your span. Next thing that I want to talk about is feature testing macros. So these allow you to check if your compiler supports certain language features or standard library features. So here are some examples of language features. You can check if your compiler supports the fall true attribute, whether it supports binary literals, coroutines, and so on. And similarly, you can check standard library feature. You can check if your implementation of the standard library that you're using supports concept, ranges, scope lock, and so on. There are quite a lot, dozens and dozens of feature testing macros that you can use. Let's have a look at a simple example here. I first check if I have an optional header. If I do have it, I include it, and then I double check if this optional header is actually defining the CppLib optional. And if that is the case, then we have optional. If we don't have the optional header, then we check if we have maybe the experimental optional header, include it, and check again what it exactly defines. Version is a new header file introduced in C++20, and it supplies implementation-dependent information about the C++ compiler that you're using. What it contains, it depends on your compiler. Some examples are it can be a version number, copyright notice, and so on. One thing that is required for this header to include is it should give you support, it should give you access to the library feature test macros. So whenever you want to use these macros, you have to include this version header. constexpr functions have been added a long time ago to the C++ standard, but they allow functions to be executed at compile time, but it's not a hard requirement. Let's look at an example. I have a function here, inch to millimeter, and it's marked as constexpr. And if I call this function using a const double, everything is fine, everything will be executed at compile time. But if I call it with a double, so not a const double, but a double, then everything will be executed at runtime. I will not have any compilation error, it will just silently call my function at runtime. And sometimes this is not what you want, and if that's not what you want, you can turn your function into a so-called immediate function using the const eval keyword. So instead of using constexpr, I just specify const eval and the rest remains the same. Now, if I call this with a const double, of course, everything is still fine, everything is done at compile time. But if I call it with a non-const double, then I will actually get a compilation error because the compiler cannot evaluate this at compile time. So constinit, they help with, well, there is this thing called static initialization order fiasco. If you have dynamic initializers, well, you don't know in which order and everything will be initialized, so that's really bad. If you have constant initializers, that's okay. You know, the initializations will be okay, but they're complex rules and it's not always trivial for someone that is browsing your code to know whether some constant initialization is happening or dynamic initialization. And with the const init keyword, you can actually force constant initialization. So here I'm defining a variable a, and I require constant initialization. So if here there is some kind of dynamic initialization, then the compiler will give an error instead of giving you strange runtime behavior. Class enums, well, the class enums that have been introduced in C++11, they were strongly typed, and also you always have to specify the name of the class enum because the different values of the enum were not exported to the parent scope. And sometimes it is cumbersome. So now in C++20, you can use a using directive using enum car type suit, and then you don't have to specify these all the time. Of course, you have to be careful with using this feature. I would recommend to use this on a small scope, as small as possible, because otherwise you're exporting everything again to the parent scope, and then you might again have the problems like you have with the old C-style enumerations. Text formatting, there are two ways at the moment. In C++17, there are two ways to format text. You can use IO streams. They are safe and extensible. Extensible, you just have to overload the insertion and extraction operators. But they are hard to read, hard to localize, because there is no separation of the format string and the arguments. On the other hand, we have printf, which is not safe, not extensible. But it's easier to read because you have a nice separation between the format string and the different arguments, and because of that, it's also easier to localize. Now, std format in C++20 combines the advantages of both IO streams and printf, and the result is safe and extensible. You just have to implement a specialization of std formatter to add support for your own custom types. They are easy to use because they have a nice separation of the format string and the arguments. So that means they are also easily localizable. And the nice thing is that they're actually more performant than sprintf, ostring stream, and toString. So there is no reason not to switch to std format. Here's a simple example. I'm outputting the string CppCon 20 in a field that is 19 characters long, with the text centered and using an equal sign as the fill character. And in this second example, I'm explicitly giving indices for my arguments. So here, this placeholder is replaced with n, and this placeholder is replaced with file1.txt. And thanks to these positional arguments, localization is pretty easy. So if I translate this read 0 bytes from 1, if I translate this to Chinese, in Chinese we have to change the order of the 1 and the 0 arguments. So you just have to modify your format string. You don't have to modify the order of your arguments here. There is a new header file called numbers, and it finally defines a number of mathematical constants such as pi, e, and so on, and they are all living in the std numbers namespace. Source location. Source location is defined in the source location header, and an instance of a source location basically gives you information of a specific line number in your code, column number, gives you the file name and a function name, and you can construct one using the static member current. And this is very useful for logging, for example. Here I have a function, log info. It logs some kind of string, And the second parameter is a source location, and it has a default value of current. And the trick here is that the evaluation of source location current is actually happening at the call site. That means that location is actually filled in with the function name, file name, line number, and column number of where I'm actually calling this log. So this avoids, so thanks to this, you don't have to use any macros anymore to achieve this. Nodiscard attribute has been added to in C++11, I think, but now you can include a reason in textual form. So you can say something like no discard, and then give a reason why you should not discard this, the return value of this function. The standard library now has support for so-called bit operations, and everything is defined in the bit header. You can ask for rotating bits left or right, or you can ask to count the consecutive number of 0 bits or 1 bit, starting from the most significant or least significant bit. And finally, you can also ask for give me the total number of 1 bits in a bit sequence. Here is an example. So the first one is constructing a bit set by rotating this given bit sequence 2 bits to the left. And here we're just counting the number of 1 bits in my given bit sequence. And then there are a couple of smaller things, additions to existing functionality. So a string and a basic string and a string view now supports starts with and ends with. We finally have a contains method for associative containers. So before you always had to use either the find method or the count method to figure out if a certain key is in an associative container. Now you can just use contains. Remove, if, and unique for list and forward list. They now return the number of elements that it removed, and before it didn't return anything. But since this is just a change in the return type, this is not a breaking change. We have 2 new algorithms in the algorithm header. We have shift left and shift right. And we have also std erase and std erase if. And by using these, you don't have to use the so-called remove erase idiom anymore. You can just ask a vector, for example, erase all the elements that satisfy a certain predicate. And finally, we have 2 mathematical new functions. We have midpoint, calculate the midpoint of 2 numbers, and we have lerp to do some linear interpolation. And then last thing is there is a new unsequence policy that you can use or to pass to a parallel algorithm. And what this says is that the algorithm is allowed to vectorize its execution, but it is not allowed to parallelize, so only vectorization is allowed. So that's it. That's all the topics I want to touch today. I would like to thank Peter van Weert for reviewing these slides, and I'm not sure if we have any time left for questions, but let me switch to Remo and see if there are any questions. Thank you.